Okay, our last recording got cut off, so let's start this one over again. Again, single operand signed multiplication, operating very similarly to unsigned multiplication, our only format for that. In this case, I'm multiplying CX by AX, my understood other multiplicand. So AX has A0, which is 10 times 16, or 160. Multiplying that by CX, which is 5. I get 800, which is 320 hex. My result is going to go in DXAX. My result is 32-bit since this is a 16-bit multiplication. My result will automatically go in DXAX. The high order portion will be zeros. The low order portion will be my result. Since the high order portion is zero, carry flag, overflow flag will both be 0. Okay. Two operand format. In this case, the normal rules for multiplication that we've learned so far are different because remember, now both both operands are, this operates a little bit more like normal addition subtraction would, where in this case I'm going to be multiplying value times ECX, but ECX is also my destination. So I am multiplying the double word at value, which is 10, times ECX, which is 10 times 16, or 160, and I get 1600, which is 640 hex. Okay, so my result is automatically going to go in the destination, which is 32 bits. Fortunately, my answer fits in 32 bits, so 0, 0, 0, 0, 0, 6, 4, 0, and I didn't overflow. In other words, the size of my result is not larger than the size of either operand, so carry flag and overflow flag will be cleared. Okay, let's look at one where we look at three operand format. Remember, in this case, a couple of things. DX is only the destination. These are the two things that are going to get multiplied together. So the word at value, that value at that place in memory called value, is 00F8, which equals 248 times 100, and I get 24,800, which equals 60E0 hex. Okay, so DX is going to hold my result. Fortunately, it just holds my result, 60E0, and again, I haven't overflowed, so carry flag and overflow flag are both cleared. Okay, so that kind of gives you a feel for how those, how the various unsigned multiplication works versus the three formats of signed multiplication. These guys spend a little extra time reading through the rules for how to use these. That's going to come in handy because I'm going to expect you to know how to use them, when to use which of these instructions. So, back to an earlier example we did in class, we multiplied x plus 1 times 2, or we doubled it. And the way we did that is we added it to itself. But what if we needed to do something? When would I need to use multiplication rather than addition? And here's what I would do, okay? I would evaluate what else you could have used. And in this case, I could use IMUL EBX times ECX, okay, if EBX holds my value in it, or I could do IMUL, not that, EBX times some immediate value, 2 if we wanted to, or 32, okay? But which of these is the better choice? I would say to you that If I'm going to add, if I'm going to double something, that's adding it to itself. So I've got something in EAX, if I add it to itself, it doubles it. If I add it then again to itself, it quadruples it, and so on. So I'm increasing it by powers of 2. But if I just need to add the same value, then I could look at this in a couple of different ways. So let's go back to a time when we used to worry about clock cycles and bytes of memory. Clock cycles we don't worry about so much because they really have become unimportant in pipelined architectures or multi-core processors, where it's not a critical factor anymore. Of course, we always want our code to be as efficient as it can, but clock cycles is just not nearly as important as it once used to be. But just to illustrate, let's talk about the differences here, okay? When I add EAX to EAX, that's going to take 1 clock cycle and 2 bytes of memory, okay? So really, that's pretty awesome. IMUL EBX is going to take 10 clock cycles, okay? Bytes of memory, it'll take just 2, so that's not as bad. So even now, I can look at this and say, okay, if I'm worried about clock cycles, if I have a non-pipeline or a single core processor and I still worry about clock cycles, then it looks like if I'm going to be adding something to itself, and clock cycles or time is the critical factor, then I can add something to itself up to 10 times, and it's until it gets less efficient to do that, then use IMUL. Remember though, if bytes in memory is what I'm going to be concerned about, every time I have an add, I'm adding 2 more bytes of memory. Okay? Now, again, we're in a day and age where we're not as concerned with how big our code is than we used to be, for the most part. But there are special cases if I am writing code for an embedded system, for example, or something that doesn't have a lot of, or any, random access memory. I can't store things. Then I have to be very careful with the number of bytes in memory each one of these is going to take. Well, just to compare or complete the analysis, for 2-operand format, it's going to be 10 clock cycles, 3 bytes in memory. Okay, that grows, by the way, as we get into 3-operand. But again, in class we'll do this where we actually will do that same example that we finished with at the beginning of Chapter 4. But now let's go back and instead of adding, let's use multiplication. And with that, we will call that a video, and we'll hit division in the next one.